Welcome all. So, last time we saw the solution of the spring mass damper models. Hopefully, you have practiced it and you are conversant with the system. So, today we will move ahead and look into the other aspects of this week. Okay. So, we will be looking into the what is known as the honeycomb systems. Okay. The name derives from the hives of the bee. Okay. So, structurally if you see, this form comes from the beehives. Okay. It follows a similar pattern as a beehive. Okay. So, it has a hexagonal cell geometry. Okay. So, there are different cells like this. Okay. So, different cells are there which are arranged in a regular pattern. Okay. And due to this arrangement of the cell, the name honeycomb comes from. The behavior can be isotropic or anisotropic. Okay. So, the relative density governs the entire properties. Okay. So, the Young modulus is directly related to the relative density, and the plateau stress, the maximum stress is also related to the relative density, and it is given by this power law. Okay. And the specific energy absorption is in the order of 40 to 60 kilojoules per unit mass of the system. Okay. And it has a very wide application in the aerospace structure and blast resistance panels. Okay. The key thing here is that due to this geometry, it has a very high energy absorption capacity, and plus in the same time the energy absorption capacity is more, S is more, and this is lightweight also. Okay. So, the total specific energy absorption capacity becomes relatively high. Okay. So, this is a very efficient material and it has found its application in different things like aerospace and the blast resistant panels. Okay. So, here we will look into the energy absorption of this material. Okay. So, here you can see phase wise from 0 to 7 the deformation that is occurring in the material. So, here this is in the undeformed shape. Okay. Here you see the deformation progressing in the total system. Okay. So, these are the different stages. Okay. So, the initial stage it looks like this. At first stage the elasticity, it is still in the elastic phase. Okay. After there the plasticity occurs. Okay. Here you can see the total plastic regime is very large. Okay. So, the total energy absorbed by this system is the area under this curve, and this is also very large. Okay. And this material is made from a simple aluminum. Okay. So, similarly this thing can be constructed using steel also and other material also. Okay. So, in this case this experiment shown is made by aluminum. Okay. And this is the configuration of this cells. Okay. So, similarly like honeycombs, foams are also used as an energy absorbing material. Okay. So, there are different types of foams, they can be made by metal also and they can be made by polymer also. Okay. So, different types of foams are readily available with different gradation of energy absorption capacity. Okay. So, the same nature follows, first the elastic phase will occur and there will be a large plateau curve. Okay. So, similar to the honeycombing also, as the energy is applied this will densify. Okay. So, the energy absorption capacity of foam also follows the similar nature. Okay. There will be a large plateau nature, and the initial energy absorptions will occur. Okay. So, the densification strains occur at 50 to 80%. Okay. And here also we can see the specific energy absorption. Okay. So, this value is for an aluminum foam and this is also comparable to the honeycomb system. Okay. And mathematically we can model this system using Cowper-Simmons model, and many other mathematical models are also very readily available. So, this is one of the models used for modeling the foams. Okay. And the good thing about this model is that it has a strain rate sensitivity parameter also. So, this model can be used for the high velocity events like impact and blast. Moving ahead. Okay. So, here we can see a typical aluminum foam. Okay. And as shown earlier, we can see the very large plateau region where here the densification is going to occur. Okay. So, the densification occurs, and owing to the large area under this curve, this material, the foam, also absorbs a lot of energy. Okay. So, one characteristic of any energy absorbing materials will be that the plateau region will be very large. Okay. The total strain will also be very high, and the deformation that it undergoes will also be large. Okay. Thereby, the area under this becomes very large, and the total energy absorption per unit mass, okay, becomes more. Okay. So, this type of material are efficient in energy absorption. Moving ahead. Okay. So, what are the different impact responses and the failure modes? Okay. So, the strain rate effects are there. Okay. Shock wave propagation results in hardening of the material. Okay. It has a low relative density. So, owing to the low relative density, the compressibility is very high. Okay. And it has a longer plateau, and normally the failure model occurs by cell buckling or fracture of the composites. Okay. Either the cell is going to buckle or fracture will occur in the material. Okay. So, one more example of this type of system is for the rock fall. Okay. So, what happens? Okay. If we travel by any roads in any hilly regions, our country, okay, this north and northeast regions consist of Himalayas, which are our relatively new mountains. Okay. And there are other plateaus in the south, and there are other plateaus in the western region also. Okay. So, in all these regions, since our hills are very susceptible, the rockfall occurs, okay, regularly. Okay. So, during the month of monsoon or during other months also, there is a constant falling of the rocks. Okay. So, this type of materials, okay, can also be used for mitigating the rockfall hazards. Okay. So, they have an application of mitigation in the rockfall hazards. Okay. So, structure are made of this interconnected steel rings. Okay. So, they are nothing but 5 to 10 mm wires, okay, and they are anchored to this slope. So, this is the anchor. So, energy absorption occurs due to the plastic deformation of the rings and the friction at net rock interface. Okay. So, here it can withstand an impact energy of 100 to 5000 kilojoules. Okay. So, we can configure this nets, okay, we can configure the sizes, we can configure the die of the wire, and we can configure this anchoring so that it absorbs very high energy. Okay. And we know that the failure strain of the steel is very large. Okay. So, this forms a very efficient rockfall protective measures. Okay. So, these are the different examples of the energy absorbing devices. Okay. Okay. So, we are looking into an example of this net design. Okay. So, this can be used as an example also. Okay. So, we can take the energy of the falling body, we can treat this as a rigid mass. Okay. So, it can be treated as the rigid mass with velocity occurring. Okay. We can assume this thing falling from a height of, let us say, 50 to 100 meters. Okay. And using this kinetic energy, okay, we can design this system to absorb the total energy. Okay. So, this is an example using 3.5 mm steel rings. Okay. So, by calculation we can show that it absorbs this amount of energy, okay, that is from a 1.5 ton rock falling at a speed of 15 meter per second. So, in order to give you an idea of 1.5 ton, normally a car weighs around 2 tons. Okay. So, to give an perspective, so this can stop a falling car. Okay. And velocity 15 meter per second, this is approximately around less than 60 kilometer per hour. Okay. So, this netting system can stop a moving car, okay, at a speed of approximately 60 kilometer per hour. Okay. So, basically what we are trying to say is that this netting system can stop a speeding car in a highway. Okay. So, now you can realize the efficiency of the system. Okay. We can optimize the ring to diameter ratio, and optimally it falls around 8 to 12, okay, to account for the strength and deformability. Okay. The slope angle is normally kept more than 45 degrees to reduce the rebound. Okay. If it is less than 45 degree, then the chances of rebound are there. Okay. So, this is kept more than 45 degrees. Okay. And the different failure modes are ring fracture at welds, anchor displacement. Okay. So, under high energy, this type of failure modes will occur. Okay. Okay. We can also look into the packaging materials. Okay. Normally, the energy absorbing materials are used as a packaging material. Okay. So, this type of things, whenever we receive something by courier, okay, we will always see that things are very neatly packed inside the foam type of system. Either it will be thermocol or some other foam type of system, especially when we are receiving some electronics or some high value equipments. So, there will be very neatly encased in foams. Okay. So, normally PU or PE or EPS foams are used. Okay. So, different types of foams are used, okay, and they have a relative density in the range of 0.02 to 0.2. Okay. So, in the stress strain range, elastic range is around less than 5% and plateau is around 5 to 70%. It means that the elastic range is very less, but the plateau range is very high, okay, and densification is around 70%. Okay. Okay. And it also has a specific energy absorptions of 10 to 60 per unit mass, okay, which is again a very high number. So, this type of things are used for cushioning and impact protection in packaging. Okay. So, these are the different examples of the energy absorption materials that are commonly used. Okay. One more example of an energy absorption materials is the vehicle interiors. Okay. If you closely look into the interior of the vehicle, there are different mechanisms, okay, that are in place to protect the occupant also and to protect the vehicle also from an impact. Okay. So, we will look into the different components and the criteria according to which they are designed. Okay. So, their focus are in the knee, headliners and the back pillars. Okay. So, they have to protect our body, the spinal cord system, our heads and the knees. Okay. So, the energy absorption capacity of this materials is around 40 to 80 kilojoule per unit mass, and they are governed under the head injury criterion. HIC is the head injury criteria. Okay. So, this number should be less than 1000 and the chest should undergo a deacceleration less than 60 G. Okay. So, these are the medical constants that are used to design the systems and to check the efficiency. Okay. So, normally when this car is tested, okay, these systems are monitored and seen whether the dummy that is placed in order to check this system, they have a head injury criteria of less than 1000 and chest deacceleration is less than 60, then only these things are considered a good energy absorbing system. Okay. So, the primary goal is to reduce the energy during occupant. Okay. So, let us look into this type of system. Okay. There is something called an auxetic structure. Okay. So, we will talk about that. So, this is a chair, okay, in which normally a person will sit, but during the crash demonstration a dummy is used. Okay. So, normally what is going to happen is that during an impact, okay, the head is going to hit this thing. Okay. So, this chair is designed so that this head injury criteria is less than 1000, okay, and the deacceleration which occurs in the chest is less than 60 G. Okay. So, this back of this seat will have a panel. Okay. The interior will be made of an auxetic structure, okay, and it will be held by some sort of framing system. Okay. So, what happens during an impact? So, impact mitigation is governed by the soft response of the global bending. So, when the impact occurs, okay, what is going to happen is that there will be a global deformation of the entire system. Okay. So, this global deformation is there so that the total energy is dissipated by the entire system. Okay. A large area is engaged in dissipating this total impact, okay, so that the net effect of the impact is mitigated. Okay. After that, there is a hard response. Okay. So, here comes our auxetic deformation. Auxetic deformation simply means that normally what happens if we are going to compress a body, okay, if it is compressed from one end, there will be an elongation in the other end. Okay. So, this effect is due to the Poisson's effect, okay, and this is denoted by the Poisson's ratio. So, traditionally the Poisson's ratio is positive. It means that if the compression occurs in one direction, the expansion will occur in the other two directions. Okay. In an auxetic material, the reverse will occur. There is a negative Poisson's ratio. Okay. So, during the negative Poisson's ratio, what is going to happen is that if there is a compression, okay, from one side, the other sides will also get compressed. Okay. So, this type of materials are known as the auxetic materials, okay, which has a negative Poisson's ratio. Okay. So, in the negative Poisson's ratio, okay, so due to this effect, okay, you can see if there is a compression in this direction, in the other direction also the compressive forces will act. Okay. So, this will result in the energy absorption in our system. Okay. So, if we open up our this system, okay, it will look something like this. Okay. There will be this plate, okay, which is given here, and there will be this honeycomb type of system, okay, which will behave as an auxetic member, okay, and this is the seating frame that will hold the structure to the ground. Okay. And the efficiency of this entire system will be governed by this head injury criteria and the chest deacceleration criteria. Okay. So, here we can see a very nice example, okay, of different types of materials, okay, combined together to act as an energy absorption system. Okay. So, in a vehicle there are other systems also. So, we just looked into one of the component here. Okay. So, the same logic is being used to design the other parts of a vehicle also. Okay. So, what you can do is that you can also look into other parts of a vehicle or any other system and break down into different components and look into the total mechanism. Okay. This can be worked as a small project also, okay, to understand the behavior of the energy absorbing materials. Okay. So, moving ahead. So, when we started this chapter, okay, we were talking about the guardrails also. So, here you can see an example of a corrugated guardrail. Okay. So, if we travel by any highway on the sides, we can see this type of corrugated guardrails being placed. Okay. So, they are designed to maximize the energy absorption capacity. Okay. So, they are made of W beam steel. Okay. So, these are nothing but this steel members which are 2 to 3 mm thick. Okay. And they can also be made from wood also, okay, and other energy absorbing materials also like bamboo and other things. Okay. So, the energy absorption criteria comes from the plastic bending of the corrugations, okay, and the deformation is more. Okay. So, for steel also we know that the plateau region is very high. Okay. So, any other material can replace this steel guardrails also as long as this energy absorption criteria is being satisfied, meaning it has a longer plateau. Okay. So, depending upon the design, they are designed for a threshold value of 50 to 80 kilonewtons, okay, and their deflection limit is 1 to 1.5 meter for vehicle redirection. Okay. So, what happens is that it has to sustain a direct hit also and it has to sustain a angular hit also. Okay. And what will happen during impact is that it will deform okay, and it will try to deflect the vehicle to a safer distance, okay, and also absorb the impact energy given by this large plateau region. Okay. So, these are the different applications of the energy absorbing materials and the properties that we have seen. Okay. So, depending upon the chosen criteria, the thickness, the configuration of this type of members are being designed. Okay. As we saw from the rockfall mitigation, as we saw from the protection of the humans, and this is for the protection of the entire vehicle. So, different criteria are used for different cases. Moving ahead. So, let us look into some of the examples. Let us say we have a beam and it can form one plastic hinge during loading. Okay. So, let us say that we are dealing with this type of beam, okay, and plastic hinge forms. Okay. So, traditionally plastic hinge we have learned in this way. Okay. There will be two structures and it will be joined by a pin, okay, and at this juncture movement can take place. Okay. It means that this thing can rotate. Okay. So, this is the traditional definition of the plastic hinge. In case of a simple structure, we define the plastic hinge such that if we cut the cross section out here and if we look into the beam, then the entire region has undergone the plastic regime. Okay. So, in the beam what will happen at the cross section? In the cross section, first as we increase the load, okay, the maximum strain will start to form. Okay. So, strain will start like this, sorry, strain will first start like this, okay, then the strain will grow, okay, and it will reach the elastic strain. Okay. After the elastic strain has reached, okay, then it will propagate further in the cross section. Okay. So, once the entire cross section has undergone plastic limit. Okay. So, at this phase, okay, we say that our plastic hinge has formed. Okay. So, for any regular structure, this is the meaning of the plastic hinge formation. This is not going to occur, okay, but it is said that a plastic hinge has formed. Okay. So, this is the meaning of the plastic hinge. So, let us say that the plastic moment capacity is given by this quantity, MP is 100 kilonewton meter, okay, and the hinge rotation is 0.5 radians. Okay. So, we have to calculate the total energy dissipated by the formation of this plastic hinge. Okay. So, let us look into that. So, solution, this is the plastic hinge moment, okay, rotation, number of hinges is 1. Okay. So, the total solution is sum total of all the plastic hinge. Okay. So, only one plastic hinge is there. So, it will be from only one quantity. Okay. If there are 2 or more plastic hinges allowed, then it will be MP of MP, and here we are not using the sign. So, it will be MP 1 theta 1 plus MP 2 theta 2 and so on and so forth. So, in our this particular case only one plastic hinge is allowed. So, this will be the solution. Okay. So, here we move into one more question. So, in this case there are 3 plastic hinges. Okay. So, all the plastic hinges have same moment capacity, okay, 50 MP. Okay. So, this might occur during a fixed beam. So, in a fixed beam we can have 3 plastic hinges. Okay. So, here the all the plastic hinge capacity is same. Okay. So, the rotations allowed are different. So, theta 1, theta 2 and theta 3. So, the total energy dissipation is required. Okay. So, following the same step we calculate all the energy. Okay. So, we know our solution is D equals to summation of MP mod of theta I So, here it will be MP1 theta 1 plus MP2 theta 2 and MP3 theta 3. Okay. So, MP is same. So, 50 comes common and rotations are 0.02 plus 0.03 plus 0.01. Okay. So, we can calculate the individual energies also, okay, or we can directly calculate like this. Okay. So, the total amount of energy dissipated by this system is 3 kilojoule. Okay. So, for a real life application, let us say that this denotes a fixed beam. So, in a fixed beam, if a plastic hinge occurs, okay, then for this particular case, energy of 3 kilojoule is being absorbed. Okay. Moving ahead. So, next question. So, here we have an elastic perfectly plastic beam in the elastic region. Okay. So, this is thing. Okay. So, the beam remains in the elastic region. It is given that the elastic moment is 80 kilonewton meter, elastic curvature is given by this number and the current curvature is this number. Okay. So, it is being asked whether the beam is still in the elastic range. So, we will have to comment, okay, depending on the current curvature, that whether this is in the elastic range or it has passed in the elastic range. Okay. So, let us look into that. The given elastic moment is 80 kilonewton meter. Okay. The elastic curvature is 0.001 radian per meter and the current curvature Kc, let us call it Kc, is 0.005 radian per meter. Okay. So, we will use this relationship. Okay. So, using this relationship, we found out that the current moment is 40 kilonewton meter. Okay. So, since K is less than K, beam is still in the elastic range. Okay. So, we can just simply comment from this thing. Okay. So, since K is less than K, so beam is still in the elastic range and the current moment occurring in the system is 40 kilonewton meter. What does it mean? Okay. Let us say we have a beam. Okay. Let us say we have a beam. Okay. And it is undergoing deformation. Okay. It is undergoing deformation and we are measuring the moment versus the curvature. Okay. So, we are measuring the moment versus the curvature. Okay. Here this limit is given as 80, okay, and the curvature is given as 0.001. Okay. Now, it is told that in the current stage my current curvature is 0.005 radian per meter. It means that the beam is still in the elastic range and the corresponding moment, okay, this was M elastic and the current moment is 40 kilonewton meter. Okay. So, this is the meaning of this question. Okay. So, moving ahead, we will do one more question. So, here we will deal with a vehicle bumper. Okay. So, a vehicle bumper is nothing but an energy absorbing system. Okay. So, it is given that the vehicle kinetic energy is 15 kilojoule, bumper has 2 plastic hinges. Okay. So, now 2 plastic hinge can form in this system. So, each hinge plastic moment is 120 kilonewton meter and the total rotation per hinge, okay, total rotation per hinge is 0.06 radian. Okay. So, it is being asked how much does the energy each hinge absorbs and what happens to the remaining energy. Okay. So, we will keep this thing as a practice question. Okay. Try to do this question, okay, as a practice question, and in the next class we will show the results and then we can compare whether we have learnt or we need some more revisions. Okay. So, I will stop here. Thank you.